Okay, so now let's talk about a local symmetry. So an example of local symmetry is the following. Let's imagine that the theory is invariant under phi of x going into phi primed of x, and phi primed of x is equal to e to the I alpha of x at phi of x, and phi star of x is sent into phi star primed of x, which is equal to e to the minus I alpha of x phi star of x. So here the big difference is that now alpha depends on x mu. So this is the crucial difference. When we had the global symmetry, the law looked very similar, but alpha was independent of x mu. Now for the local symmetry, alpha depends on x mu. So that is the key difference between the two transformations. It's still an internal symmetry because the field and the transform field live at the same space-time point. So why would we make a distinction between these two? Well, when we're talking about a global symmetry, Newton's theorem gives us a conservation law. What Newton's theorem says is that for every global symmetry, you get a conservation law. So Newton's theorem is telling you statements about continuous global symmetries. Of course, not discrete global symmetries, but for continuous global symmetries. And we are talking about a continuous global symmetry here because alpha is a continuous uh, number. And you know it's global because alpha is independent of x mu. It turns out for a local symmetry, there is no conservation law. There is no conservation law at all. And when we prove Newton's theorem, we'll be able to see why we don't get a conservation law when you've got a local internal symmetry. Global symmetries are very different to local symmetries. A global symmetry, an example of that is a translation. If you have a particle sitting somewhere and you do a translation, the particle actually moves. So the global symmetry maps one physical state into another physical state. So the global symmetry is a map between physical states. The local symmetry is not a map between physical states. If you perform a local symmetry transformation on a physical state, you get the same physical state back. So local symmetries reflect redundancies in our description. They are not transformations on physical states. Now I want to illustrate this a little bit because this is a really important point. Um, Actually, let's record a few things here. So for the global symmetry, we should really say it is a map between physical states. That's an important thing to record. So it's a map between physical states. And for the local symmetry, as opposed to this, it is a redundancy. That's an important thing to record. And then perhaps another very important thing about a global symmetry is that this leads to a conservation law. So that's the global symmetry, and the consequence of that is a conservation law. The local symmetry, you don't get a conservation law. You should really think about this as a redundancy in our description. You know, it's like we're using too many variables to do the description, so a physical state can be represented in many different ways because we've got many different ways to write it down. Good. Okay, and finally, let me just introduce maybe one other piece of language. When we talk about a local symmetry, we mean the same thing when we say a gauge symmetry. So gauge symmetry is the same thing as a local symmetry. Okay, good. So those were a couple of important points. Now I want to illustrate this a little bit more. Um, Let me maybe say one more thing. It's a redundancy in our description. Also, it does not lead to the conservation law. So that's another important thing to bear in mind. Good. Now, what I want to do is I want to illustrate the fact that if I perform a local transformation on a physical state, I don't change the physical state. I'm not going to illustrate that in general. We will talk about this in general later, but right now, I just want to illustrate it with a simple example. So the one place where you really have already studied local symmetries, that I'm going to come back and use this, is electromagnetism. So this should be familiar to you. Now remember, in electromagnetism, you have a four potential. You have a mu, which is phi, and a vector potential A. You can write this in a more relativistic notation where we write A naught and AI, and I goes over 1, 2, and 3. And in electromagnetism, we have a local symmetry, a gauge symmetry. And how this acts is A mu is taken into A primed mu, which is equal to A mu plus D mu chi. Now, it is true that the gauge potential has changed, but the gauge potential is not physical. So even though A mu has changed, the quantities which are physical, the electric field and the magnetic field, those you could actually observe, those are actually invariant. So let's ask ourselves now, or let's remind ourselves of this. So let's say, how does the electric field and the magnetic field transform? We'll continue in a moment.